Welcome to my talk. Today I'm going to talk about our paper, Photo Localization for Declarative Models in Alloy. I'm Kai Yuan. This is a joint work in collaboration with Alison, Darko, and Safraz. Here is the roadmap of my talk. First I'm going to talk about the motivation, and then background, example, methods, metrics, evaluation, and finally the conclusion. Declarative specifications are maddening harder to learn and even harder to debug. So we want to develop an automatic technique that can help developers debug their code. Our focus in this paper is Alloy modeling language. We choose Alloy because it is widely used in many systems. For example, it is used in understanding the UML diagrams, analyzing firewall configurations. It is also used for security policies, network switches analysis, and web security. Alloy is a relational first-order logic with transitive closure. Photo localization is a well-studied area in software engineering. Researchers have developed two major types of techniques: the spectrum-based photolocalization technique and the mutation-based photolocalization technique. The spectrum-based photolocalization technique computes a suspiciousness score for each code element based on the code coverage and a suspiciousness formula. In general, code covered by fewer passing and more failing tests is more suspicious. Mutation-based photolocalization technique computes a suspiciousness score based on the mutations and a suspiciousness formula. After each mutation, the technique will run all the tests against that mutation, and mutations that makes more failing test passing while preserving the passing test results are more suspicious. A-Unit is a testing framework for Alloy. It defines the Alloy test cases, which is the foundation of our technique. Alloy predicates or assertions are treated as Alloy test cases. The expect clause specifies the expected test case satisfiability. A-Unit brings a traditional form of testing from the imperative world to the Alloy world. Alloys also have a built-in mini-set solver, which is able to highlight expressions for which no satisfying Alloy instance exists. So the mini-set solver can only find an unset core when the executed command is unsatisfiable. We build a baseline technique on top of the mini-set solver with unset core. For each Alloy AST node, we count the number of unsatisfiable failing tests whose unset core includes that AST node. The AST nodes that are highlighted more often by the unset core ranked at the top. Here is an example Alloy model that specifies the Java class hierarchy. The class signature defines a set of class atoms. Each class can extend at most one class. The object class is a singleton. The predicate object no extension specifies that the object class should not be a subclass of other class. The cyclic predicate specifies that the class hierarchy cannot have loops. The all extension object predicate specifies that any class that is not the object class must transitively extend the object class. Finally, the predicate class hierarchy joins all the previous predicates. And when running this class hierarchy predicate for up to 3 atoms for each signature. On the right-hand side, we specify two tests. Test 1 is an invalid class hierarchy, and it is expected to be unsatisfiable. Test 2 is a valid class hierarchy, and we expect it to be satisfiable. Here we show a faulty Java class hierarchy model that are written by a student. We highlight the faults in red. On the right-hand side, we have two tests written in A-Unit style that represent the instances of the previous slide. We do not show more tests because of space limit. Our baseline model based on Alloy's built-in unset core would highlight the entire predicate or extend object as faulty. In comparison, our technique would accurately highlight the faulty node because when we mutate this node, many of the failing tests pass and passing test results are preserved. The baseline technique cannot highlight any node in this predicate object no extension because there is no unsatisfiable failing test that covers object no extension predicate. Our technique is a hybrid technique that are built on top of two other techniques. The first technique is a spectrum-based photolocalization technique that does the coverage analysis at the Alloy paragraph level. Because Alloy does not have a control flow, all the ST nodes in an Alloy paragraph are either executed altogether or not executed at all. Alloy paragraphs that are executed more often by the failing test and less often by the passing test are more suspicious. The second technique is a mutation-based photolocalization technique that defines a set of mutation operators. The technique mutates each AST node and then then run all the tests to do mutation analysis and assigns a suspiciousness score for that mutant. Mutations that makes more failing tests to pass and preserving the passing test result are more suspicious. So finally, our hybrid technique would leverage both the score from the spectrum-based and the mutation-based techniques. And then it ranks the AST node in descending order of the computed suspiciousness score. This slide shows all the suspiciousness formulas that are used in computing the suspiciousness score for both mutation-based technique and spectrum-based technique. In general, AST nodes that are covered more often by the failing test and less often by the passing test are more suspicious. The mutants that kills more failing tests and fewer passing tests is more suspicious. Our spectrum-based localization technique is called Alloy FLco. It is built on top of a static analyzer. The static analyzer binds a variable usage to its signature and binds a function call to its declaration. In that way, the analyzer is able to find all the covered Alloy paragraphs transitively for each test. The analyzer ignores dependencies that are never used. For example, given a formula for each S of type S and T of type T, such that there exists some S, and the predicate P with parameter S hold. In this formula, T is never used, so the analyzer will not consider T as covered by the test. Finally, the analyzer would let us know for each paragraph what are the passing and failing tests that covers it, and the technique would compute a score based on both the coverage information and the suspiciousness formula. The mutation-based localization technique is called Alloy FLmu. It defines a set of mutation operators for different types of AST node. The technique mutates individual AST nodes using appropriate mutation operators, and after each mutation, it runs all the tests against that mutant and computes a suspiciousness score for the mutated AST node. If an AST node has multiple mutations, the maximum suspiciousness score will be assigned to that AST node. All non-mutated descendant AST nodes share the same suspiciousness score as the root mutated AST node. The technique only reports mutated AST node, and the reported AST node are sorted in descending suspiciousness order. This slide shows all the mutation operators defined in our mutation-based localization technique. More details are in the paper. Our hybrid-based technique is built on top of both the spectrum-based and mutation-based technique that we described before. We observe that the mutation-based technique works well in general, and the spectrum-based technique works well from omission errors. So our hybrid technique takes the weighted average of the suspiciousness scores from both the spectrum-based and mutation-based techniques. The score is equal to 1 minus lambda times the suspicious score from the spectrum-based plus lambda times the suspiciousness score computed from the mutation-based technique, where lambda is between 0 and 1. And we use the suspiciousness score of the spectrum-based technique if no mutation applies to a given node. And finally, we report all the AST nodes sorted in descending suspiciousness order. We define some new metrics to measure the effectiveness of our techniques. The main reason is that our technique reports suspicious code element at the AST node level, and AST nodes are hierarchical. Not all the AST nodes are reported by our techniques. So sometimes the faulty AST node might be reported as parents or descendants of the suspicious AST nodes, and the existing metrics cannot fairly capture the closeness between the reported AST node and the actual faulty AST node. So we define new metrics which is inspired by the nearest neighbor distance metrics in the program dependency graph. And our new metrics measure manual effort based on the closeness between the reported suspicious node and the actual faulty node. The first metric is called the nearest neighbor up and down. It takes a parameter k. So basically, this metric assumes that the debugger would look at the top k suspicious node, and essentially it assumes the developer would look at the parent and the children of the reported AST node, and then inspect all the nodes until the developer finds the first fault. So in this case, the circle in number 1 represents the first suspicious node reported by the technique. The circle with number 2 represents the second suspicious node reported by the technique. The circle with F represents the actual real fault. Suppose k equals to 2. We assume the developers will look at the top 2 suspicious nodes and then do a breadth first search, looking at the parents and the children until the first fault is found. The developers would need to inspect all the circles colored in gray, and we would report 6 in this case. The second metric is called nearest neighbor down. It assumes that the developers would look at each suspicious node one at a time. It also assumes the developer can only look at the children of the suspicious node. So in this case, case, the developer would first look at the first suspicious node and do a breadth-first search, and the developer cannot find anything. And second, the developer would look at the second suspicious node and then do a breadth-first search. And in this case, the developers would find the first faulty node, and the algorithm would stop. In this case, developers need to inspect 6 nodes, so the metric would report 6. The last metric is called nearest neighbor down worst. This metric has a similar assumption as the nearest neighbor down metric, except that it would assume that developers are unlucky and would inspect all the non-faulty nodes before the first faulty node. In this case, when developers investigate the second suspicious node, it would look at all the non-faulty children and then look at the first faulty node. In this case, the metric would return 10. We evaluate our techniques on 90 real-world faulty alloy models that are collected from past faulty alloy distributions, other related works, or faulty student solutions. Each faulty model contains one or more faults. Those faults include over-constraint, under-constraint, or a mixture of both. The tests are automatically generated using MuAlloy, which applies mutations on the correct alloy model and then automatically finds a unit test that can kill the mutant. We use the proposed distance-based matrix and the traditional top K matrix to evaluate our technique. The top K matrix measures the number of exact AST node that matches the faulty node in the top K suspicious node. We answer the following research questions. The first question is, how does the suspiciousness formula affect our technique? The second one is, how does the mutation-based technique weight, lambda, affect the hybrid technique? The third question is, what is the effectiveness of the baseline onset-based technique and the hybrid technique? The fourth question is, how does the test size affect the hybrid technique? And final question is, what is the time overhead of the hybrid technique? This table shows the average metric values over all 90 faulty models for each formula, metric, and technique. For the hybrid technique, we use the mutation-based technique weights, lambda equals to 0.4. Lower value for the distance-based metrics or higher value for the top K metrics are better. We can see that for the spectrum-based technique, Tarantula and the Barino formula works best, but all the 5 formulas give roughly the equal effectiveness. For mutation-based technique, the WuChi formula seems to achieve the best effectiveness. For the hybrid-based technique, the WuChi formula seems to achieve the best effectiveness score for the NNUD and top 1 metric. For NND, NNDW, and top 5, top 10 metrics, the WuChi formula achieve roughly the similar effectiveness score as the best Barino formula. So we can conclude that the WuChi formula performs roughly the best for all techniques. This table shows the metric values for various mutation-based technique weights, lambda. The hybrid technique uses the WuChi formula by default based on the previous research question. We can see that when lambda reaches 0.4, almost all the metrics give the best result, except top 5 and top 10 metrics. The top 1 metric is more important than top 5 and top 10 metrics. So the best mutation-based technique weight, lambda, should be 0.4. These two tables show the average distance-based metrics and the sum of top K-based metrics over all 90 faulty models. It also shows the number of times each technique performs the best among all the 4 techniques in each metric. We can see that the hybrid-based technique performs the best on average for all the distance metrics, and it performs the best for the top 1 metric. So we can conclude that the hybrid technique is the best among all the 4 techniques, and it performs significantly better than the baseline onset core-based technique. This table shows the effectiveness score for various test ratios for the hybrid technique. For each round, we sample 10%, 20%, 30%, up to 100% of the test suite, and making sure that the larger test set always subsumes the smaller set. For example, the 20% test suite would include all the tests in the 10% test suite. And then we compute the average effectiveness score for each metric. And then we repeat this experiment 10 times and take the average for each ratio. We can see that when using the full test suite, the hybrid-based technique gives best results. So we should always use the full technique, because more tests often mean that the hybrid technique can give better result. This table shows the average time overhead in seconds over all 90 faulty models for each technique. We can see that the baseline onset core-based technique and the spectrum-based technique are much faster than the mutation-based technique and the hybrid technique. Although the difference is significant, the mutation-based technique and the hybrid-based technique only takes around 30 seconds, so it's not too expensive and they would give much better result. So their time overhead that is acceptable compared to the baseline techniques. In conclusion, we proposed a hybrid photolocalization technique, which is the first AST node level photolocalization technique for Alloy that leverage multiple tests. We also defined the distance-based metrics at the AST node level to measure the effectiveness of our hybrid technique. And we evaluate our hybrid technique on 90 real 40 models and showed that the hybrid technique is a lot more effective than the baseline on-set core based technique. And finally, we open source our technique at the following URL. Feel free to check it out. Please feel free to reach out if you have more questions.